This video is sponsored by KiwiCo. A few videos back I built this cute little 3D printed remote control hydrofoil. It served as a small scale test platform for what I'm going to build in this video, which is a giant version with a 2-meter wingspan that I can ride on. I was blown away by how stable and controllable the small scale model was. If the large scale version performs anywhere near as good as this, I'll be stoked. So where did my desire to build a rideable hydrofoil come from in the first place? Last year after Open Sauce in San Francisco, I got the chance to check out the new Navier N30 electric boat with James from Project Air and Peter from Peter Streeple. It's a 30-foot fully carbon fiber hull with 3 retractable hydrofoils that allow it to fly above the surface of the water. This makes the ride extremely smooth even in choppy seas. Riding on the N30 was awesome, but I had even more fun riding on their little hydrofoil John boat. This thing served as a small-scale test platform that they used to develop their flight control system before moving up to the N30. It just so happened to use the exact same electric motors and ESCs that I used to use on my 13-foot Boston Whaler, so it was cool to see what kind of performance I could have gotten if my boat had hydrofoils, and weighed a lot less. After riding this thing around, I knew I wanted to build a manned hydrofoil craft of my own. I didn't quite have room in my workshop for a John boat-sized build, so I decided to instead base mine off an 11-foot stand-up paddleboard. And eventually the design came to basically just be an extra large e-foil board, but one that you sit on instead of stand, because I want it to be self-stabilizing, not human stabilized like most other e-foil boards out there. For this I would use the exact same Dreamflight code that I had used on my smaller scale test platform. I actually kind of started this project several years ago by experimenting with 3D printed hinge designs in airfoil profiles. They turned out to work really well and were super easy to produce, so this is what made me end up wanting to 3D print the entire wing and horizontal stabilizer. 3D printing also made it super easy to add all the little things, like servo mounting spots, wire channels, spar channels, attachment points for the tail booms, and so on. The main foil has 2 ailerons, 2 big waterproof servos to control them, 2 extruded aluminum masts that connect to the paddleboard, and 2 attachment points for the tail booms, or fuselages as they're called in the foil world. If we split it in half, we can see there are slots for an aluminum main spar and another aluminum alignment rod back here. In the back we have the horizontal stabilizer. It's held to the main wing with these 2 square 30mm carbon fiber booms. It has 2 elevator sections, each with its own servo. The whole thing is a symmetrical airfoil that gets really fat around the big servos to keep it as streamlined as possible. The servos were too thick to entirely embed in the main wing as well, so to streamline those and reduce drag I just made separate servo covers for them. The push rods and control horns are going to be similar to any old RC plane, just beefier. They stick out quite a bit and are definitely not the most hydrodynamic things in the world, but this is going to be a slow hydrofoil. Hopefully slow like my prototype was. Probably not that slow, but still hopefully pretty slow. I'm wanting it to be like the bush plane of the hydrofoil world. And at slow speeds, having draggy control horns isn't as much of an issue. If we were aiming for higher speeds, I would definitely want to find a way to make the control linkages more streamlined, but it shouldn't matter as much on this build. By the way, if you want to have a look at this CAD file, you're in luck. The whole thing was designed in Onshape, which means it lives in the cloud, and it's just a click away. Use the link in the description to sign up for a free Onshape account, and you'll be able to download the files or edit them to suit your needs. If this wing was solely 3D printed, it would obviously just break since it'll be carrying probably over 200 pounds. So to help with the forces, I had the mast connected to some 1/4-inch aluminum plate that I had cut by PCBWay. The plate is welded to a square aluminum spar that runs through the length of each wing. If I were redoing this project, I would definitely change the way the spar and mast connector works, but for now this is the way it is. I got my roommate Ethan to TIG weld the spar to the mast connector plate. That worked pretty well, but I did have to hammer the spars back straight because they did warp quite a bit. Next up, it was time for a crap load of 3D printing. I printed pretty much this entire thing on the Prusa XL out of PETG. For a lot of the complex inner geometries, I used the multi-extruder capabilities to print PLA as the support material. It doesn't stick to PETG, so this makes removing the supports easy. Now most hydrofoils are made of carbon fiber because it's super stiff and can be made to have a super smooth surface finish. 3D prints are neither of those things, so my plan was to add a layer of fiberglass over the wing after it was all assembled. This would be fairly easy to do on the wing, but I obviously wouldn't be able to get fiberglass into the 3D printed hinges, so I was just going to leave that as raw plastic. I used a gyroid infill for the whole thing, and this was for a very specific reason. I initially wanted to keep each wing section airtight so that they would have some buoyancy. This would make the vessel pretty unstable while at a standstill, but while moving, the buoyancy in the foil would hopefully reduce the stall speed quite a bit. Having buoyancy in the foil was one of the reasons why this smaller version was able to go so slowly. So airtight prints was the hope, and I had pretty good luck achieving this on the Prusa XL in the past. But I also realized that most of the time FDM prints are not airtight. Fiberglassing over the surface would have fixed this, but I wasn't going to be able to fiberglass over the hinge portion, so they were still vulnerable to potentially leaking. If I were to have used one of the normal infill patterns, there would have been a good chance that individual cells filled up with water, and in this case it would be a total pain in the ass to get all the water out. I chose the gyroid infill because it makes the entire inside of the 3D print one continuous volume. This way, if a wing segment leaks, I can drill a little hole in it and the water will flow out when I bring the hydrofoil out of the lake. I even decided it would be a good idea to put drops of blue food coloring into the prints, so if the wing segments did fill up with water, I would more easily be able to tell, with the help of some backlight. This ended up being a huge mess, but for now the prints seem to be turning out pretty good. I did test some of the sections, and at first they seemed airtight, but after holding them underwater for several hours, the food coloring made it obvious that they did leak. So this kind of ruined my dreams of a buoyant foil, but at least now it won't capsize when it's not moving. So after weeks of printing, I got all the pieces made, so it was almost time to start the assembly. But first, let's talk about the servos. These are the actuators that move the ailerons and elevator, so I can control the hydrofoil. I chose to use these giant high-tech D845WP servos. They have an IP67 rating, which means they are protected against short periods of immersion in water while under pressure between 15 centimeters and 1 meter. On the hydrofoils, they aren't going to be any deeper than a meter, but I was a bit sketched out by the short periods part. So while they could have held up to water ingress on their own, I decided to play it safe and design an additional layer of protection. Here's what I came up with. There's an aluminum shaft that transfers the rotational movement from the servo spline out to the servo horn, and 2 resin-printed enclosure halves that seal the servo in. The aluminum shaft goes through the enclosure with a bearing here and 2 O-rings here to hopefully keep out water. I got the aluminum shafts CNC machined by PCBWay as well, and they came with a sandblasted surface finish. I wanted the area that goes through the O-rings to be smooth, so I threw them in my lathe and polished them with increasingly finer and finer sandpaper until they were, well, not perfect, but definitely smoother than before. Those got screwed onto the servo hubs, which then got attached to the splines. I SLA printed the housing shells out of clear resin on the Formlabs Form 4, and tapped some holes in them. You'll see why in a bit. The servos just fit right in there, and the wire pass-through hole gets silicone squirted around it, and then sandwiched in place by a little plate with a groove. Next, I lubed up the shaft with some silicone grease. I chose silicone grease so that it wouldn't degrade the O-rings or any of the other plastics. I popped a bearing into the upper part of the housing and put some grease behind that, and then put in the 2 O-rings with as much grease as possible around them. To join the 2 housing halves, I siliconed around the rim, and then carefully slid those together while making sure the O-rings stayed in place. The 2 halves are secured together with long M3 screws, so I put some nuts in the nut-shaped slots and tightened down the screws. Earlier, I tapped a hole in the side for a vent with a flathead screw to close it. For this next step, I had to remove the vent screw. Now here's the key to this design. I screwed a grease nipple into the servo housing and connected that to a grease gun. This allowed me to pump silicone grease into the gap between the servo and the housing, and hopefully form a fully watertight barrier around the servo. There was a delicate balance between the pressure needed to fill all the cavities and the pressure needed to just blow up the housing. So I just covered the vent hole with my finger and gave it a few extra pumps to hopefully allow the grease to fill all the voids without cracking the housing.
Oh yeah, it's pressurized, baby. Oh, I can see the O-rings getting greased. Ready, set, fire in the hole.
Wow, it really did fill in all the holes.
Then I could remove the grease gun from the grease nipple and put the vent screw back in to hopefully lock in the grease for good. During the design, I tested a lot of different sizes of control horns to perfectly match the full range of motion of the servo with the full range of motion of the control surface. This is really important because we want to get as much torque as possible into the control surface. But more importantly, if the servo were to have enough range of motion to max out the control surface throw, then it would probably just break everything. So I was careful to design it so that nothing would max out, even throughout the full 1000 to 2000 microsecond range of the PWM signal. I'm using these shaft collar flange hub things that are left over from the Snowcat project. They hold the servo horn onto the servo shaft. The servo horn is this short stubby little carbon piece that I cut on the CNC router. Once I figured out the right geometry, I CNC cut the control horns out of 4mm carbon fiber plate and screwed those onto one of the elevator sections. All the elevator sections slide onto carbon fiber tubes with Gorilla Glue in between. The sections of the main wing fit together in the same way. They all just slide onto the spar and are held together with Gorilla Glue. I used small carbon tubes as alignment pins to keep the sections perfectly aligned as the glue dried. So after I came to realize that the 3D printed wing segments were not going to be watertight, I decided to make it easier for water to flow through the entire wing so that it would drain more quickly when I pull it out of the lake. To do this, I cut away the outer shell near the leading edge of each section. This way the infill of each section is connected and water can drain through the entire thing. Here's some of the horizontal stabilizer sections going together. Same as everything else, those just slot onto 6mm carbon alignment rods. And then once the Gorilla Glue had cured and foamed out, I shaved off the excess with a razor. The elevator then just slides onto the horizontal stabilizer. It's super simple, and the hinge is very robust and low profile. I was really happy about this part of the design. Next it was time to install the servos and control linkages. I'm using some nice ball joints with M5 threaded rod. The ball joints just screw onto the servo horn with a nut on the back. The servo wires were going to have to travel a long ways, so I soldered on some thicker gauge extensions and pulled those through. The servos themselves just screw into place with thread-forming screws on each side. The control rod then screws onto the control horn, and with that the linkage is complete. Here it is wiggling. And then I installed this cover over the servo to make it more streamlined. Next it was time to mount the aileron servos in the main wing. First I had to route the wires through, and then the servos just pop into place, and are secured with thread-forming screws. The pushrod came after that, same as before. And we can see it wiggles very well, no problems there. These servo covers attached over the servos to make them more hydrodynamic. It was SLA printed on the Formlabs Form 4 that came out a few months ago. This thing prints super fast, so it's great for big parts like this. Finally, this hydrofoil is starting to take shape. Ooh wee, look at that. This thing is huge. Now let's redirect our attention to the board. This thing is 11 feet long, but it really doesn't need to be that long, so I decided to cut the back off. This would make transportation a bit easier and reduce the weight a little bit, but other than that, cutting it was probably not entirely necessary. The wood layer in between the foam and epoxy skin was soggy and delaminating, so this board was a great candidate to get cut up. To hopefully fix the delamination, I injected Gorilla Glue in there. My plan was to cap the back with some fiberglass, so the first step was to fair the surface a bit and cover up some of the holes and valleys with fairing compound. Then I gave the edge a slight fillet so that the fiberglass cloth would more easily adhere to the contour. And the fiberglass cloth is exactly what came next. I mostly used 7-ounce cloth, but I used a few layers of 2-ounce on the edges since it conforms so much more easily. Now I need to make the part that attaches the board to the foil masts. I'm using a section of this 2x12 piece of wood, and I marked out all the drill spots with a mostly 2D, 3D printed stencil. These are the holes that the mast base plates will screw onto. And then I also cut some notches to reduce weight, since this was quite a thick and heavy chunk of wood. Probably way overkill, but whatever. That whole thing got a quick sanding to smooth out the sharp edges. The thought of building a giant hydrofoil from scratch like this probably seems like a really daunting task for most people, but for me it totally seemed doable, and that's only because I started small and slowly worked my way up to bigger and bigger projects throughout the years. For me, this journey started early, and I'm really grateful for that, because I feel like starting young really helps you build an intuition for how things work in the physical world. One of the best things you can do for kids is to get them to start building things at an early age, and that's where KiwiCo can help. KiwiCo Clubs offers 5 programs for kids of all ages and interests that guides them on a journey of hands-on learning. I got the chance to try out the Maze Arcade Kit. It includes all the pieces needed to build an interactive maze game that was super fun to play. Building it will give kids experience with motors, wiring, switches, batteries, and other materials that even I use in a lot of my projects on this channel. The KiwiCo Club that excites me the most is KiwiCo Labs. This teaches kids to engineer things like games and robotics in a fun and interactive way. I'll bet that we can find a similarity between this kit and the hydrofoil project. Yep, I'm pretty sure the little DuPont 1P electrical connectors they use here are the same ones that I used to connect the sonar sensors to the Teensy board for the hydrofoil. Let's see, I'm pretty sure these little connectors right here are the same. See, they really are the building blocks for the projects I'm doing today. All you need to do to join a KiwiCo club is pick the one that best fits your child's age range and interests. Then sit back and wait for your first crate to show up in the mail. You can visit kiwico.com/rctestflight and use discount code RCTestflight to receive 50% off of your first month of a monthly subscription. Big thanks to KiwiCo for sponsoring this video. Now let's get back to building the hydrofoil. Next we'll direct our attention to the masts. I had to cut some holes in the side for the phase wires to fit through. Here are the mounting plates that hold the masts onto the board. These were clearly not made for e-foils because there were no holes for the phase wires, so I had to make them myself. These are the times when I wish I had a mill. This was pretty painful, but eventually I got some holes big enough for all the wires. Before mounting the masts to the wing, I had to do some soldering. This was so that the aileron and elevator servos could share common power wires. Fewer wires make it easier to route them all through the masts. This is where I really needed that heat shrink with hot glue built in, but I didn't have it, so I just tried to get as much silicone as possible under the heat shrink. I'm still to this day not entirely sure if this method worked very well. But anyways, those wires got routed up through the masts, and then the masts got glued onto the wing. Don't worry, it also got screwed into the aluminum base plate in the bottom, but I did later realize that I shouldn't have made the base plates completely stick through the bottom of the wing like this, so that's why I'm also gluing the masts in place. Then I glued a cover over that. I also made a nice fillet with fairing compound around the masts and hoped that it would help share some of the load and stiffen things up. Now it's motor mount time. The orange is PETG and the yellow is TPU. The yellow part is what will hug the mast, so I was hoping that it would provide a bit of vibration damping. So the phase wires go through the rear mount part, and then they go through the mast, and then come out the other side. The motor mount then just slots over the mast, and the front part goes on with 4 long-ass screws that go all the way into the motor. The wires that go through the mast then go through the mast mount, as with the servo wires. The mast mounts then get screwed onto the mast. I'm using the same FDM printed propellers that I initially made for my electric Boston whaler. So here's where we are so far. Looking good. Next, it's time for the tail booms. I'm using these waterproof connectors to make the horizontal stabilizer removable for transportation. I also soldered matching connectors onto the main wing side and routed those wires through. That was before the mast had been attached. To fasten the booms to the wing, I'm going to glue in these little pieces of carbon plate with M3 press nuts in them. Those just got glued in right under this hole I drilled. That press nut is in there so that a screw can go through this hole and hold on to this boom. Now it's back to that big piece of wood. I glued some T-slot nuts into it just because they're the only nuts I had that were gluable. Those are for the bolts that hold the masts onto the wood. Now it's time to put the wood onto the board. Step 1 was to remove the foam, and man, what a pain that ended up being. This was some tough foam. The paddleboard had a curved top, so to give the big piece of wood a flatter surface to sit on, I glued some smaller pieces of wood to the rails. And then once the glue dried, I sanded the top of that down so that it was flat. Same with these other pieces of wood I glued on there. I kept sanding and checking over and over again until the big piece of wood laid flat. Then finally I glued the big wood to the little wood. But don't worry, this glue isn't the only thing that will hold me up. Here you can see how I used some Depron foam sheet to build a little wall that lies tangent to the edge of the board. Then I laid some carbon fiber tow down that wraps around the big wood and drapes over the edge of the board. My entire body weight and the weight of the board and the battery is going to be hanging underneath this wood, and these carbon fiber strands are going to be what's supporting the majority of the weight. I also laid 7-ounce fiberglass cloth over pretty much everywhere else on the joint between the wood and the board. After sanding the edges of the tow down smooth, I added a few layers of 2-ounce glass to that whole area. This will just help keep the tow locked down and make the whole area smoother. Now to put my fabrication skills to the test. Will the wood just rip off the board when I stand on it? Nope, seems like it's plenty strong. It felt super solid. Then I painted the wood and fiberglass white to protect the epoxy from UV rays. Now back to the main wing. I used my CNC router to cut 2 strips of 4mm carbon fiber plate. These slot into the main spar and connect the 2 wing halves together. There's also an aluminum rod at the back that helps with alignment. Here's a random elevator servo cover getting glued onto the horizontal stabilizer. Remember how I said I was going to fiberglass over the entire wing? Yeah, well, I ended up just kind of shifting it into quick and dirty mode and skipping that part. However, there was one area that definitely needed some reinforcement, and that is the area between where the tail booms connect into the wing and the masts. There's no structural frame that connects the tail boom directly to the mast. They're both just connected with 3D printed parts that are glued together. So to prevent this area from just ripping apart, I'm laying some fiberglass down. This will hopefully kind of create an exoskeleton that locks the plastic together. I also wrapped some carbon fiber tow around the edges, so that should add a good bit of strength. Despite this, I was still quite skeptical of whether or not it would hold up.
That's some flex there for sure. God damn, this thing is pretty janky.
Next up, it was time for the battery box. I wanted to make it really big so that it would fit a 100 amp hour 24 volt lithium iron phosphate battery. It's pretty simple, just a box made out of 1-inch XPS insulation foam. And that whole thing just got glued onto the back of the paddleboard. I made some nice straps out of this super flexible Fiberflex 40D filament. Those get paired with some other parts to make these simple latches that keep the box lid closed. The motors and ESCs on this hydrofoil are the exact same ones that used to be on my electric Boston whaler. They're Vesk 75200 ESCs and FlipSky 65121 motors. The flight controller and radio literally came straight off the small-scale test platform. After setting up all the actuators and servo endpoints in Dreamflight, I was able to wiggle the control surfaces. Since the elevator was split anyways, I decided to just make it elevons instead of elevator only. And here you can see that when I wiggle the IMU around, the control surfaces are moving to try and stabilize the vehicle. Once this whole thing is assembled, it's going to be really big and heavy. Definitely too much for one person to lift, so I designed some removable wheels that will attach under each wing. I'm printing these things on the new FL Sun S1. The main selling point of this printer is that it's super fast. And by golly, they're not kidding. This thing was a giant part, printed with relatively dense infill and thicker outer walls. Despite this, it only took about 5 hours. This would have taken like 16 hours or more on any of my other printers. Some lawnmower wheels just bolt onto the 3D printed parts, and they just hug the bottom surface of the wing and leading edge. That allows you to lift the nose of the paddleboard and move the whole thing around really easily. At this point, I had finished mounting all the electronics to the board and set up differential thrust for yaw control. And that pretty much concludes the majority of the build. There's a few more things we'll add later, like the sonar sensors and a seat, but for now it's ready for a preliminary test. I broke it all down, put it in the back of the truck, and headed to the lake. This first test will be with IMU-based attitude stabilization only, no active height control.
It's pretty heavy.
Quiet hydrofoil flies under the water, doesn't make a sound. It's a real life magic carpet ride.
PB Bridgers, hit me up.
This video is long enough already, so I'm going to save the test flights for the next video. But in the meantime, here's some other hydrofoil footage. I got the chance to try out the Hydroflyer, which is an e-foil board with handlebars. The handlebars make it much easier to learn. This was my first time trying it out, and I pretty much instantly got the hang of it. They also make it easier to find your balance point, which is really important. With normal e-foil boards, it takes a while to figure out exactly where to stand, but this one doesn't have that problem. Another benefit of the handlebars is that you can catch air. If you were to do this on a normal e-foil board, you'd almost definitely fall off when it lands, because the foil just stalls and the whole thing nosedives. But with the handlebars, you can just ride it out and then pop right back up. Pretty fun. Thanks to Ansel for the FPV footage, and to Jerry of Hydroflyer for letting us try it out. That's all for this video. Stay tuned for the next video to see my big homemade hydrofoil fly all around the lake. Thanks for watching. Bye.
The quiet hydrofoil flies under the water, doesn't make a sound.